Hello, welcome to Lecture 5 of Parallel Computing. So today we're going to talk about how to write parallel programs for distributed memory machines using MPI. So first of all, let me remind you about the distributed memory architecture. So if we look at the diagram on the left over here, then the distributed memory architecture is that we have a number of different processors, right, these PE things, and each of the processors has its own memory, which it can access. However, if a processor wants to access memory from a different processor, then the processor needs to send a message over a network, right? And the other processor receiving that message will get the data from its own memory and then send it back to the initial processor. Okay, so this is called distributed memory processing. I want to also look at the diagram on the right. So here, what we have is a combination of a distributed memory architecture and a shared memory architecture. Okay, so what's happening over here is that we have these nodes, and each of these nodes has multiple CPUs in them. Okay, and the nodes has this piece of memory, and all of the CPUs in a node can access any piece of memory from this chunk of memory. Okay. However, if a CPU from one node wants to access memory from a different node, then again, it needs to send a message over a network. Okay. And then the receiving processor will fetch that memory and then send it back to the first processor. Okay. So this would be and then within each one of these nodes, what we have is a shared memory situation. Okay, because all of the processors within a node can access any piece of memory in its own chunk of memory. Okay, so within a node we have shared memory, but across different nodes we have distributed memory. And so today we're going to talk about how to program these distributed memory machines. So basically, the language we're going to use is just standard C or C++ or Fortran. Okay. And so these languages don't actually support distributed memory operations. And so therefore, to do these operations, we're going to have a library for doing the distributed memory communication. And so there are actually a number of different libraries that one can use, but the most standard one, the one that's used by far the most, is called MPI, which stands for Message Passing Interface. Okay, so this library was developed by academics and industry back in the 90s. Okay, so back in the early, or before the early 90s, there were a number of different competing methods for doing distributed memory programming. So it was quite a messy situation because all of these different programs written using the different libraries were not compatible with each other. Okay, so eventually people got together and said that they wanted to standardize this process. Right? They wanted to have one library that everybody would use for doing distributed memory processing. Okay, and so there are several goals that they had in mind when they developed this MPI. Right? So first of all, they wanted MPI to be as portable as possible across different architectures. Okay, so of course, when you implement MPI on different architectures, you have to take into account the special characteristics of that architecture. But at least they wanted people to be able to write the same code and for that code to compile on different architectures. Okay, they also wanted to make MPI as efficient as possible. Okay, so so they added various functionalities for efficiency. And they wanted to make MPI a very general and flexible library so that you can write basically any type of distributed memory program that you want. Okay, so there are several versions of MPI. So the first version lasted from basically the mid-90s until about 2008. Okay, and then since then, they've been updating MPI. So MPI version 2 came out in 2008, and MPI version 3 came out just a few years ago in 2015. Okay, so MPI is actually an interface, right? So it's a library with a bunch of functions that you can call. And the MPI specification is about the functions that you have to support in the library. But it's not about how to implement these functions, okay? And so different vendors, when they implement MPI, they will tailor the implementation to their own hardware to make it as efficient as possible. However, all of the vendors, as long as they support MPI, they support the same programming interface, so that a program that you write for MPI really is portable because you can take the same code and compile it on different types of hardware. Okay, so there are a couple of flavors of MPI which are pretty popular. So one of them is called MPI-CH. So this is made by Argonne National Laboratory. And another MPI implementation is called OpenMPI. Okay, and there are also commercial implementations from these various hardware vendors like Intel, Microsoft, and so on. Okay, so what does an MPI program look like? So there are basically 4 types of functions that, that exist in the MPI interface. Okay, so the first type of function is for process creation. So this is basically just to start up your program. Okay, so we need various functions to initialize the program. The most important functions in MPI are the ones that let you do these distributed memory operations, right? So remember that these operations are basically sending and receiving messages from remote processes. Okay, so the most important functions in MPI are all about how do you send and receive messages from other processes. And there are 2 main types of these communication functions. So there are the point-to-point functions, and there are collective communication functions. So point-to-point just means that you're sending or receiving messages between 2 particular processes. Okay, so it's going from one process, one point, to another process. On the other hand, the collective communication means that you're actually doing communication among a group of processes. So for example, you might be broadcasting to a group of processes. Okay, so this would be a collective communication. So in the rest of this lecture, we're going to be looking at different types of point-to-point and collective communication functions. Okay, so so I just want to stress again that in order for processes to get data from other processes, there's no way for a process to directly read data from another process. Okay, it has to be done through sending and receiving messages, and so you could right. And this is sort of in contrast to the shared memory programming model, where all of the processes share a common chunk of memory, right? And then any process, in order to access this memory, it can just do a normal read or write operation. Right? So a shared memory program basically looks just like a traditional C program, right? In order to read some memory, you just you can read and write memory using the normal C assignment and read operators. Okay, now having said that, the newer versions of MPI do want to support both distributed memory the distributed memory programming model, and they also want to make it easier to write shared memory style programs. Okay, so the newer versions of MPI that have come out within the last 10 years or so, they have support. They have some partial support for shared memory programming. Okay, it's still not quite the same as actually doing shared memory programming, but it makes it easier to write this style of programs. Okay, but predominantly when people use MPI, it's to do these message passing type programs. Okay, so so now the third type of functions for MPI are you can define data types in MPI, new data types. So MPI supports all of the basic data types like floats and ints and chars and so on, but you can also define new data types. Okay, so there are functions for doing that. And the final type of function for MPI are the ones that, so you can use them to create these things called communication groups. Okay, so communication group is basically it's a set of processes that can communicate with each other. Okay, so whenever you do communication within MPI, you have to specify which group you're communicating with. Okay, and the groups are useful as a way of organizing the communication within MPI. And then, so there are functions in MPI to create these different communication groups and to structure them in some way. Okay, and there are also ways for you to sort of specify like a topology on this group. Okay, so for example, you might say that a group of processes, they have a mesh type topology. Okay, and once you specify this topology, then MPI can do some optimizations in terms of its communication. Okay, so so now we're going to talk about these different types of functions, and we're going to start with the process creation functions. Okay, so all right, so before we do that, we actually have to talk about what is the process model for MPI. Okay, so MPI uses a model called SPMD, which stands for Single Program Multiple Data. So what that basically means is that for an MPI program, of course, it's a parallel program, so you're going to run this on multiple processors. However, all of the processors, they're going to be running the same piece of code. Okay, so so in this figure on the right over here, right, we have a piece of code in the source file, right, and then we compile it, right, and then so this produces one executable, and then in order to run your program in parallel, you send the same executable to all the different processes. Okay. Yeah, so we have a single program running on different processors. But of course, you don't want all of the processors to do exactly the same thing, right? That would be just duplicating the same work over and over. So you you want them to run the same program, but you want them to operate on different pieces of data. So that's why it's called multiple data, right? And the way that you can have these programs work on different pieces of data is that all of the processes have an ID, or each of the processes has an ID. Okay, and then within your program, your MPI program, you can specify that different processes will do different things based on their ID. Now, I just want to mention that SPMD is actually very different from something we've seen earlier, which is SIMD, okay? So remember that SIMD stands for Single Instruction Multiple Data. Okay, now the SIMD is basically, this is more of a hardware architecture. So, and what it's saying is that you have multiple processing units, but they're doing exactly the same instruction at the same time point. Okay, so in SIMD, all of the processors are synchronized with each other, and they're doing exactly the same instruction. Okay, in MPI, the the processes are running the same program, right? But there's no synchronization. There's no implicit synchronization between the processors. Okay, so one processor can be at one point in the program, and another processor can be at a completely different another point in the program. Okay, so even though they're running the same piece of code, there's no synchronization between them. So this is very different from SIMD. Okay, now when you have a processor, so that processor can actually run multiple processes. Okay, so so let's say that you have let's say 10 processors and then 20 MPI processes. Okay, so you could actually put 2 of these processes onto each processor. Now, usually when you run MPI, you don't really do this. Okay, usually you just you run the same number of processes as you have processors or as you have cores. Okay, so if you have 10 cores or 10 processors, you're only going to run 10 processes, 1 per core or process. Okay, now sometimes, and the reason for doing this, the reason for not putting too many processes onto the same processor is that you would get resource contention if you run many processes on the same processor. Right? But sometimes if you have processes which do very little amounts of work, okay, then in those cases, you might actually want to put several processes onto the same processor, just so that you can fully utilize that processor. Okay. There's this issue of how do you map processes to processors, right? So this is something that we talked about a few lectures ago. And in MPI, the programmer doesn't really have any control over which processes get mapped to which processors. Okay, so next, let's actually look at how to create processes in MPI. Okay, so the first thing you need to do is, if you want to use MPI, you have to include the MPI header library. Okay, and then next, in order to start your program, your MPI program, you need to call the function MPI init. And then after you're done using MPI, you need to call MPI finalize. Okay, so now here's an example, a simple example program. It's basically a hello world program in MPI. Okay, so the first thing we do is we include the MPI header. Right? And then now we have these two variables here. So the first one is the number of processes. Okay, and the second one is the rank of the process. Now the rank of the process, remember that we said we want different processes to do different things based on their ID. Okay, so the rank of the process is basically their ID. Okay, and the ID is simply a number between 0 to the number of processes. Right, so if you have 8 processes, then the ranks of these processes are just numbers between 0 to 7. Okay, and every process has a different rank. Okay, now if you want to run MPI, the first thing you need to do is call MPI init. Okay, and you call these with your arguments. All right, so next, so in this hello world program, all we want to do is we want to figure out how many processes there are, right? And then we want each process to print out its rank. And so what we do is we call this function called MPI com size. Okay, so now what this com is that I mentioned earlier that let's see, where was this? Okay, yeah. So if we look over here, right? So in order to do communication, you have to specify a group of processes that you want to communicate with. Okay, and this group of processes is called a communicator. Okay, now when MPI starts up, right, by default, there's going to be, MPI will build you a default communicator, right? And that's going to consist of all of the processes that you started your MPI program with. Okay, so if you start the program with, let's say, 8 processes, right, then your default communicator is going to have those 8 processes in them. And the default communicator is going to be called MPI com world. Okay, so therefore what this line is doing, MPI com size, right, what you're saying is tell me how many processes are in this communicator MPI com world. Okay, and then store that in the variable npes. Right, so npes is going to be the number of processes that you're running with. And now MPI com rank, right, this is going to tell you, so remember that we're running this program on multiple processes, right? So each process, when it does this command over here, when it calls this function, right, this is going to get that process's own rank. Okay, so if you call this with 8 processes, right, and if I'm process number 5, then my rank is going to become 5 over here. Okay, and again, you need to call this with MPI com world because you need to say which group of processes am I looking for my rank within. Okay, so if you have multiple communicators, then the same process could actually have different ranks in the different communicators. So here we're just looking at the default communicator that MPI creates when you call MPI init. Okay, so then once you get your rank and your npes and your number of processes, right, you simply say that, so from process, so whatever your rank is, you say from this process, out of the total number of processes, you say hello world. And then after that, we're going to close our MPI program by calling MPI finalize. Okay, so that's the basic hello world program. And if you want to run this program, okay, then after you install MPI, you can just type something like MPI run, and then you could have a host file here, which tells you who are all of the processors that you're allowed to access. Okay, it's basically on your network, right? You have multiple computers, and you can list those computers in the host file, and then that will run the MPI program on those computers as long as you have permission to them. Okay, and then this MP thing here specifies how many processes you want to create. Okay, so for example, you might want to create might want to run 8 processes. Okay, and this myprog, right? So this is just the program that you created over here. And then when you run this, what's going to happen is on the host that you run this command from, right, you're going to see these messages being printed out. These are from process something out of something, hello world. Okay, and the total number of messages you see is just how many processes you started. So if you start 8 processes, you're going to see 8 of these messages. Okay, so they're basically going to say like from process 0 out of 8, hello world, from process 1 out of 8, hello world, and so on. Okay. However, the messages don't have to appear in the order 0, 1, 2, 3, and so on. They don't have to appear in the order of the rank. Okay, and this is because once you start these processes, then, as I said, there's no synchronization between the processes. Okay, so some of them can run fast and some of them can run slow. So the fast ones are going to be the ones that print out the printf message first. Okay, so you could very well see something like, you know, from process 5 out of 8, hello world, and then maybe from process 2 out of 8, hello world, or something. Okay, so there's no order, no particular order on how these messages get printed out. Okay, so that is I talked about the SPMD model, which is the single process model that MPI uses. Now, before I go on, I just want to mention that there is another model which can be used for distributed memory programming, and that's the MPMD model. Okay, so this just stands for multiple programs, multiple data. Right? SPMD is single program, and this is multiple program. Okay, so this just means that you have multiple processes, but each one of the processes runs a different program. Okay, and the way these MPMD programs usually work is that they take something called a master-slave approach. Okay, so that means that in the beginning you just have one process. Okay, and this is the master process. Okay, so the process is just executing by itself. Okay, and at some point, maybe the process finds that it's got a lot of work to do, so it wants to do this work in parallel. So at that point, it calls a spawn operation, which creates other processes. Okay, so those are the slave processes. And the slave processes are going to help the master do the work. Okay, so this is in contrast to the, and the code that the slave processes run, right, the program that they run can be different from the master processes program. Okay, so that's why it's called multi-program, right? And then also, so that's one difference from MPI or the SPMD model. And the other difference is that with MPI, you start all of your processes at the beginning. Okay, so if you want 8 processes, then from the outset, you have 8 processes. On the other hand, for the MPMD model, right, we said that initially you start with 1 process. And then at some point, when you want more helper processes to help you do some work, right, you can spawn more processes. Okay, so the number of processes can vary over time. And it's the processes are created dynamically. Okay, so then you're going to pay some overhead for creating these processes. Okay. On the other hand, the MPMD model might somehow be kind of a more natural way to program things. And there are libraries that support the MPMD programming model. So, for example, something called PVM. Okay, so that's one way to program in this model. Okay, but as I said, MPI is by far the most popular way to do distributed memory programming, and so we'll be focusing on MPI. Okay, now, right, so this kind of summarizes what I said earlier about the types of different MPI types of MPI functions. Okay, so actually MPI has many, many functions. It's got hundreds of functions. Okay. However, if you want to write a efficient and very general MPI program, you actually don't need to know all of the functions, right? It suffices to know just a pretty small subset of these functions, and that takes you a long way in terms of writing programs. Okay, and these functions, so we have functions that help initialize the program, right? We have functions for doing point-to-point communication. So these are like send and receive functions. Okay, we have these collective communication functions. So that's where you communicate with a group of processes, right? You can either do broadcast to them, or you can do these operations called scatter or gather or all-to-all, reduce, scan, barrier. We're going to talk about all of those later. Okay, you have ways of creating new data types. Okay, so these are called derived data types. So you have things like contiguous or indexed or struct or vector and other data types. Okay, and then you have ways of creating and structuring communicators and also defining virtual topologies. Okay, so we're not going to go through all of these functions, right? So I'll show you examples of each type of function, but we're not going to go through all of them because there are many of them. So if you want a very complete look, then you can just look at the documentation for MPI, for example, at this URL. Okay, so let's talk a bit more about communicators. Okay, so communicators. So another name for them is communication domain. Okay, so it's just a set of processes that can communicate with each other. Okay, and when you write a program, you can actually have multiple communicators, right? So you can take your processes and break them into multiple groups, right? And then each group can communicate with each other. But one process can actually lie in several groups at the same time. And again, the reason that we want to have these communicators is to help organize our communication. Okay, so so like to give you an example, suppose we have let's say a grid of processes. Ooh, okay, so sorry, what's okay, all right. So suppose we have a grid of processes like this. Okay, so let me just draw a grid of processes, right? Then you might want to define a communicator, which first of all includes all of the processes. So that could be one communicator, okay? But then you might also want to define a communicator, which maybe for each row, right, of processes, right? So we have 4 processes here. Maybe you want those to be another communicator. Okay, because sometimes you don't want to communicate with all of the processes in the mesh. You just want to talk to processes in your row. Okay, so you can create multiple communicators like this, right? And then sometimes you might want to talk to, you know what? Let me switch to a different color. This is kind of hard to see here. Just give me a second. All right, so we could have the row communicators, right? And then maybe sometimes you want to talk to processes in your column. Okay, so then you can define some column communicators also, right? So you see that by having these communicators, it makes your communication much more organized, right? Because when you just want to talk to your column, right, you can just use your column communicator and not the entire communicator. Okay, so communicators have a type which is MPI com. Okay. And then whenever you do a communication, any type of communication, whether it's a point-to-point or collective or anything, you have to specify a communicator. Okay, and then when you call MPI init, right, this automatically creates a communicator for you, a default communicator, which is called MPI com world. Okay, so the communicators have sizes. Okay, so if you take a communicator, right, and then if you call MPI com size, right, then you get back the size of that communicator in size, in the variable size. Okay, and then within each communicator, each process within the communicator has a rank. Okay, and so if your communicator has 100 processes, right, then your rank is going to be a number from 0 to 99. Okay, and again, the rank, the reason it's useful is because it lets you differentiate between different processes. And so that way different processes can do different things. Okay, so even though everybody's running the same program, they do different things based on their rank. Okay, so next, let's see how we can actually send messages. Okay, so that's the most basic operation in MPI, is just to send a message. Okay, to do that, we're going to call this function MPI send. Okay, so this has a bunch of arguments. Let's see what these arguments are. So first of all, the data that you want to send. Okay, so you're going to give a pointer to this data, and the data is going to be stored in this address buff. Okay, so starting from this address buff, right? This is the data that you plan to send. Okay, and then you need to say how many data items you're sending. Okay, so this count is so for example, if you're sending let's say ints, right? If you're sending 10 of them, then your count is 10. You need to specify the type of data you're sending. Okay, now you need to give the MPI data type, which is so MPI has built-in data types for all of the classic data types like chars and ints and so on, right? So you can give one of these data types, or if you're trying to send, if you've defined your own data type and you're trying to send something with your own data type, right? Then you can also put that that type over here. Okay, now since we're sending, right, we need to say where we're sending to. Okay, so this destination is the rank of the process within our communicator. So we have a communicator that we're sending to, right? And then we have to know the rank of the process within this communicator that you want to send to. Okay? And the final thing is that you have this tag here, and yeah, and the tag is used to differentiate between multiple messages that you send to the same destination. Okay, so if I send you 10 messages, right, then I'm going to tag them so that you can tell which one is which. Okay, and then between a pair of processes, all the messages that are sent and received between this pair, they're processed in FIFO order. Okay, so the first message that I send is going to be the first message you receive. Okay, so next, so we talked about how to send messages. Next, we look at how to receive messages. So here, you're going to call the MPI receive function. Okay, and again, this has a number of arguments. And so what these arguments are is, so this buffer is, again, this is a pointer to a memory location. And this is where you're going to store the data that you receive. Okay, so you have to pre-allocate this buffer to store the data. Okay, and you need to say what type of data you expect to get, right? So that's the type over here, and then how many of these data types you plan to get. So if you're going to get like 10 ints, right, you need to say 10 and then MPI int over here. You also need to know who you're receiving from. Okay, so so the source, so the source is a process in this communicator COM. Okay, and you need to give the rank of that source within this communicator. Okay, and because the source can be sending multiple messages to you, right? You need to you should specify the tag of the message that you plan to receive. Okay. Now sometimes you can give this value here MPI any tag. Okay, so this says that I'm going to receive a message from the source, and I don't care what the tag is. Okay. However, if you give a specific tag here, if you give like a tag of 2, right, then that means that you're only going to receive a message with the tag 2. Okay. Oh, and the source, here I forgot to say that you can also, here you can specify MPI any source. Okay, so this means that you don't really care who you're going to get the message from. You'll take the message from anyone. Okay, and the final thing is we have this MPI status over here. Okay, and the status is useful when we're using these wildcards like MPI any source and MPI any tag. Okay, because when you get a message, even if you called MPI receive with MPI any source, okay, so you're willing to take the message from any process. Okay, but then after you receive that message, you still want to know which process that came from. Okay, so if you use the MPI any source, right, then when you go look in the status, right, then one of these fields in the status will tell you the actual source that you got the message from. And then if you used MPI any tag, right, one of the fields in the MPI status will tell you the tag of the message that you got. Okay, now if you have two sends which both match a receive, okay, so for example, you call MPI any source, right, and then you have two processes that both send to you, okay, so they both match what this receive requires. then you could have only one of the send complete, okay, and the other send is just lost. Okay, so now let's do an example with send and receive. Okay, so in this example, we've started out by calling MPI init, and then we find out how many, the size of our communicator and our rank. Okay, so for this example, let's assume that we only have 2 processes. Okay, so the number of tasks here is going to be 2. Okay, so the processes are going to have ranks 0 and 1. Okay, and all we want to do is we want the let's see, 0 sends to 1. Okay, yeah, so we want task 0 to send a message to 1, and then it's going to receive a return message. Okay, so 0 is going to send first and then receive later. Okay, and then task 1 or process 1 is going to receive first and then send after that. Okay, so then what we have here is if my rank is 0, then I'm going to call MPI send, right? I'm going to send just a char, right? A single char, right? Which is being stored over here, right? I'm going to set the destination to be the node with rank 1, right? So here I define my destination to be 1, right? I define some sort of tag. Let's see, yeah, so tag is 1 here. It doesn't really matter, right? And then I specify that, this destination is in this MPI com world. Okay, so that lets me send this char, which I suppose is X. Okay, and then I'm going to receive a message from the same, let's see, the same source. Right. Then I'm going to receive a message from process 1. Okay, so I send and receive from process 1. And then if my rank is actually 1, right, then I'm going to set my destination and source to be process 0. Then I'm going to first of all receive a message from process 0, right, and then I'll send a message to process 0. Okay, and then lastly, I'm going to print out. So both processes are going to print out that they received some number of characters from the other process. Okay, yeah, so that's how we use the send and receive functions. Now, we need to be careful about using these functions, though. Okay, and the reason is that the MPI send function is blocking. Okay, so what this means is that after you call MPI send, right? So now you plan to send this message, okay? And that's going to take a certain amount of time. And this function is blocking, meaning that until the send succeeds, okay, then the process that called the MPI send is just blocked, right? It's stopped. The process stops after it calls MPI send until MPI send finishes, okay? Yeah, and the reason this function is blocking is to ensure that the data is correctly sent, okay? Because remember that in MPI, the processes are not synchronized with each other. So if I'm sending you a message, right, maybe you're not ready to receive that message yet, okay? So I need to wait. So if I want to send you a message, then I start my send, but then I need to wait until you're ready to receive that message in order to make sure that you don't lose the message. Okay, if I just send you the message, right? If I sort of like mail you a letter, right? And I don't care where you are. Maybe you're on vacation or something. Okay, then that letter can get lost. Okay, so what I need to do is I need to make sure that you're ready to receive that message before I can be sure that before I can finish my function call. Okay, so now the amount of time that MPI spends blocking depends on whether your implementation of MPI has something called a hardware send buffer. Okay, so a hardware send buffer is just, it's like a location in memory, in your processor's memory, or in your process's memory, where you're going to store the messages that you want to send out. Okay, so if there is such a buffer, then MPI send is just going to wait until the data is copied from this MPI program into the buffer. Okay, once it's been copied into the buffer, then I know that my message is stored safely in the buffer, and so now my MPI send can return. Okay, and later on, MPI can actually take the data from the buffer, and once the receiver is ready, it'll send the data to the receiver. Okay, but in any case, as long as my data is in the buffer, I know it's not going to get lost. And so MPI can return after that. However, sometimes your MPI implementation, it might not have a hardware buffer. Okay, if it doesn't have a buffer, then the sender actually has to wait until the receiver is ready. Okay, until the receive has actually occurred, and then the sender gets some sort of notification. Yeah, so okay, so MPI send is going to block either just for a short time until the data is copied into the buffer, or for a long time until the receiver is ready. Okay. On the other hand, MPI receive is always going to block. Okay, because if I call MPI receive, that means that I want to receive a piece of data from somebody, and until I get that piece of data, I'm just going to keep waiting. Okay, so MPI receive is going to keep blocking. Now, sometimes you want to do non-blocking communication because you know, if your program gets stuck after calling an MPI send, then you can't do anything anymore. Okay, so instead you want to just say that okay, I want to send out a message, but then as soon as I as soon as I specify this, right, then after that I want to continue with doing some other work. And so the way that this can happen is that, yeah, so if we have the hardware buffer, right, then the process can continue with the computation from process. Yeah, okay, so if we have this hardware buffer, then as soon as I call one of these send and receive functions, then I can continue with my computation while the data is being transferred from my process buffer into this hardware buffer. However, when I do this, so I'm transferring the data from my processes buffer to the hardware buffer, I have to make sure that I don't modify the data in my process buffer, because if I modify it, then this transfer process can get corrupted. Okay. And so I need to wait until I've completely transferred data from my process buffer to the hardware buffer. So I need some way to detect when this transfer is complete. Okay, so there are functions that that help me do this. Yeah, so these are so now I have these non-blocking communication functions. Okay. So these functions are, we use them in a similar way to MPI send and receive. However, the name is just, we add an I in front of it. Okay, so MPI I send and MPI I receive. Okay, so these functions can return immediately after being called. Right? They're not going to block. But we need to know when these operations complete, because until they've finished, I can't modify the data in these buffers. Okay, so in order to know when the operation has completed, I have this function called MPI test. Okay, so the MPI test is going to take an MPI request object, right? And it's the request object corresponds to one of these calls to MPI send, I send, or MPI I receive. Okay, and the MPI test is going to tell me when this send or receive has finished, right? So now when you call MPI I send, you actually have to include the request, right? And same for I receive. Okay, and then later on, to see whether this send or receive has finished, I'm going to call MPI test with that request. Right, and then I can also wait. So maybe so maybe I need to keep waiting until this send or receive has finished. So here I can call MPI wait using the MPI request, and this is going to make the process wait until the send or receive has successfully copied over the data. Okay. Now, when we use these send and receive functions, another thing we have to be careful about is deadlock. Okay, so I'll give you some so first of all, a deadlock just means that all of the processes in your system are stuck at some point, right? Nobody can do anything. Okay, no process can take the next step. Okay, so this means that all the processes are waiting for each other and everybody is stuck. So my program is completely frozen. So this is, of course, something, a very bad thing. So we want to make sure to avoid deadlocks. Okay, so let me give you some examples of when deadlocks can occur. Okay, so the first example is, so here I have a program where I'm doing 2 sends. Okay, and another process, the one with rank 1, is doing 2 receives. Okay. However, for my sends, now these arguments, so this argument over here, so sorry, let me switch to red. So this argument is actually the tag for the message I'm sending. Okay, so I'm first of all sending a message with tag 1 and then a message with tag 2. And then this 2 over here is saying that this rank 1 process wants to receive a message with tag 2, and then it wants to receive a message with tag 1. Okay, so now this program can block if we don't have any buffering. Okay, and the reason is that if we don't have any buffering, then when I call this send, right, so I'm trying to send a message with tag 1, but there's no corresponding receive to get that message. Okay, so the rank 1 process is going to be blocked at the send over here, and the rank 2 process is going to be blocked at this receive over here, because the rank 0 process needs to finish the tag 1 send before it does the tag 2 send, right? But this MPI, this rank 1 process is waiting for the rank 2 message, right? But that's not being sent because the rank 0 process is stuck sending the tag 1 message. So if there is no buffering, then it's possible that the processes will deadlock waiting for each other. Okay. If there is a buffer, though, then probably there will not be a deadlock, because if there's a buffer, then both of these messages, okay, can be placed into the buffer, and both of them will be sent. Okay, so even though I'm placing the tag 1 message first and then tag 2, both of them go in the buffer and are sent out. So eventually the rank 1 process will receive both the tag 1 and tag 2 messages. Okay, so now in order to fix this, it's very easy. All I need to do is make sure that I send and receive in the same order of the tags. Okay, so if I send tag 1 first, right, then I should try to receive, then the other process should try to receive tag 1 first, right? And then I'll send tag 2, and then he receives tag 2. Okay, so that's one example. Another example is where suppose we have several processes and they're connected in a ring. Okay, and what we're trying to do is each process I in the ring is trying to send to the next process I plus 1, right? And it wants to receive a message from the previous process. Okay, so then a simple way to write this program would be that, so I'm going to send a message, right? So let's say I'm going to send 10 integers to the next process, right? With rank so I'm going to take my rank, right? And then add 1, so that's the next process. And I take this modulo the total number of processes. And then I receive from the previous process. So my rank minus 1 modulo and NP. Okay, now this is also going to, yeah, okay, so if we have buffering, okay, then again, both the send and the receive can complete, and we probably don't have deadlock. However, if you don't have buffering, right, then the problem is that we have these processes, right? So here, this process is doing a send. So let's write this as send 0, right? This process 1 is doing a send. Let's call that send 1, send 2, and then send 3. Okay, so all of the processes are doing send because that's the first operation they do. Okay, however, none of these sends can actually complete, right? Because the only way for a send to complete, if you don't have buffering, is for the corresponding receive to happen. Okay, but right now, all of the processes are stuck on their send, right? Because nobody's doing receive, so none of these sends can finish. So everybody is stuck on their send. Okay, so now we have a deadlock. Okay, so then how do you fix this, right? So how can you allow processes to send in a ring, but without deadlock? Okay, so the way that you can do that is instead of everybody sending first and then receiving, what we're going to do is we're basically going to have half of the processes send first, and then the other half of the processes receive first. Okay, so basically we're going to have process 0, let's say it's going to send first, right? But then process 1 is going to receive first. Okay, and then process 2 is going to send first, but then process 3 is going to receive first. Okay, so the way we write this is I'm going to look at my rank. Okay, if my rank, if I have an even rank, then I'm going to send first, right? And I'm going to send to my my next the next process, and then I'll receive after that. Okay, and on the other hand, if I have an odd rank, then I'm going to receive first, and then I'll send. Okay, so this way, again, P0 is going to send first, and P1 is going to receive. Okay, so then P0 can finish its send, and then P1 can finish its receive. And likewise, P2 is going to send first, and P3 is going to receive first. Okay, so P2 and P3 can also finish their first steps. And then after they finish their first steps, right, then we can have P1 send, right, and then P0 is going to receive, P2 is going to receive, right? So then P1 is going to send, right? So then we're going to have S1 over here, and then P2 is going to receive, right? And then P3 is going to send, and then P0 is going to receive. Okay, so after you do all of this, then you still have that every process sends to the next process and receives from the previous process. Okay, but you don't have a deadlock because you split the send and the receive into two different orders. Okay, now this program does get rid of deadlock, but it's kind of a tedious program, right? You have to think about how to write this program. And then here we have a simple ring topology. If you had a more complicated topology, then it's also more complicated to write a deadlock-free algorithm like this. Okay, so instead, it would be nice to have an automatic way to make sure that we don't we don't deadlock when we do these sends. Okay, and the way we can do this is to call a function which can both send and receive at the same time. Okay, so it's basically one function that combines MPI send and MPI receive. Okay, and there are a lot of arguments in this function, but they're basically what you expect if you want to combine the send and receive functions. Okay, so I'm not going to go through all of them. I'll just show you how you can write the previous program where you try to send in a ring, how you can write that using this MPI send receive function and not have any deadlock. Okay, so so then all you need to do is just say that I'm going to call MPI send receive, and then I'm going to specify who I send to first. So I send to the next node, and my rank plus 1, right? And then I receive from the previous node, and my rank minus 1. Okay. And then this is going to execute both the send and receive together. And so there will not be a deadlock on the ring. Okay, so now let's sort of use all of these functions in a more interesting algorithm. Okay, so let's try to put all this stuff together and see if we can actually successfully use it to solve a problem in parallel. Okay, so the problem we're going to look at is this thing called even-odd sort. Okay, so this is a sorting algorithm, and the way it works is that if we have n processes, okay, then we're going to work in n phases. So for simplicity, let's first assume that each process has a single number. Okay, so we have n numbers, and we're going to work in n phases. So we have these even and the odd phases. Okay, and in even-odd phases, we do different things. So in the even phases, right, we're going to pair up the processes in this way. Right, so basically, so the first process pairs with the second, right? We're going to pair the 1, 2 processes, the 3, 4, the 5, 6, and so on. We're going to pair these processes, and then after you pair them, each process has a number, and we're just going to make sure that these two numbers are ordered correctly. Okay, so our goal is to sort the numbers in increasing order. Okay, so for the first pair of processes, right, we see that they're actually out of order, right? 2 is less than 3, so we're going to swap them. Okay, you're going to have the first two processes swap their values. Processes 3 and 4, right, they're actually in the right order, okay, because 3 is less than 8, right? 5, 6 are in the right order, and then 4, 1 are in the wrong order, so they have to swap. Okay, so that's the first phase. Okay, now in the second phase, we're again going to pair processes, but we're going to pair the other set of processes. Okay, so previously we paired processes 1, 2, and then 3, 4, and so on, right? In the even phases, we're going to pair the processes 2, 3, right, 4, 5, 6, 7, and so on. Okay, and then after you pair the processes, again, you try to take the pair of numbers that they have and then put them in the right order. Okay, so for example, this 8 and the 5, they're out of order, so they need to get swapped to 5, 8. Okay, and the 6, 1 is going to get swapped to 1, 6. Okay, so that's the even phase. Okay, so next we go to phase 3, which again is an odd phase. Okay, so for the odd phase, again, we're going to go back to the pairing between processes 1, 2, 3, 4, 5, 6, and so on. Okay, and after you pair the processes, you're going to make sure that their values are in the right order. Okay, so for example, you swap the 8 and the 1 and the 6 and the 4 here. Okay, so then you just keep switching between the phases, between these even and odd phases, right? And for the different phases, the processes pair themselves in different ways, right? They either pair with the previous process or with the next process, depending on the phase. And once they pair with the process, they are going to swap their values if the values are out of order. Okay, so this was for the simple version of the algorithm where each process only has one value. Okay, so now you could have a more general version where each process has multiple values. Okay, so suppose, for example, process A has 4 values and B also has 4 values. Okay, so then here, instead of swapping the values between A and B, what you want is you want to take all of these values, all 8 values, okay, and you want to give the smaller 4 of these 8 values to A, right, and you want to give the larger half of the values to B. Okay, so what's going to happen is A and B are going to swap, are going to send each other their values. Okay, so A is going to get B's values and B is going to get A's values. Okay, and then now you're going to combine all of these values and you're going to merge them together, and then A is going to take the smaller half of those merged values, and then B is going to take the larger half. Okay, so so if you do this, then what you can show is that if you have n processes, right, and then if you run n rounds of this even odd sort, then afterwards you're going to have all of the values be sorted. Okay, and this is it's not a very efficient sorting algorithm, but it's a highly parallel one, right? And the reason is that in each of these phases, you see that all you need to do is pair up these processes, and then different pairs of processes can be working in parallel, right? So for example, the 3-2 pair, right, is going to work in parallel with the 3-8 pair and the 5-6 and the 4-1. Okay, so it's a highly parallel algorithm. Okay, so so we're going to try to write this algorithm in MPI. Okay, so yeah, so this code looks a bit complicated, but it's actually doing some pretty simple things. So we have a bunch of variables here, so I'm not going to talk too much about them until we get to them. So we have things, like elements or received elements and so on. Okay, so I'll talk about these as we get to them. So the program is going to start with the initialization part, right? We're going to call the com size and the com rank. Okay, we're going to malloc enough space to store all of our elements, right? And then we're going to just initialize the elements randomly, and then we're going to sort each process starts out with some number of elements. Okay, so let's say that you start out with 10 elements. Okay, so you're going to generate 10 random elements, and you're just going to sort your own 10 elements. Okay, but of course you're not sorting other people's elements yet. Okay, so our goal is to eventually sort everybody's elements together. Okay, now now here we're going to compute something called even rank and odd rank and even rank. Okay, so this is basically saying that in the even phases, right? So if we look at this diagram here, right, then in the odd phases, right, a process can either pair with the next process, right, or it can pair with the previous process, right? So so here we have processes 1, 2, 3. No, sorry. I guess the ranks are going to be 0, 1, 2, 3, 4, right? Yeah. So the ranks start with 0, right? So here, if I'm in an odd phase and if my rank is even, then I'm going to pair with the next process. Okay. But if my rank is odd, then I'm going to pair with the previous process. Okay. And then in the even phases, right? Then if my rank is odd here, I'm going to pair with the next process, right? And if my rank is even, right, like this guy has a rank of 2, then he's going to pair with the previous process. Okay, so the process that I pair with depends both on the phase that we're in and also whether my rank is even or odd. Okay, so these computations here are basically just to keep track of this these things. Okay, right, and then this is to sort of yeah, so this is to take care of communication between the first and the final processes, right? So for example, you know, the first process over here, right? If you're in the even phase, you don't actually communicate with anyone. Okay, so it's just a corner case that we need to take care of. Okay, now here, this is actually the main loop for the algorithm. Okay. And what it's saying is that we're going to run a total of n phases, right? If we have n processes, we need to run for n phases. And then if we're in an odd phase, right, then we're going to, so we want to swap these elements between pairs of processes. So to do that, we need to do both send and receive, right? And we saw that unless you do this carefully, you could get a deadlock. And so the way we avoid the deadlock is to use this function MPI send receive. Right? This is going to guarantee that we don't deadlock. Okay, so MPI send receive, but we need to know who we're sending to. Okay, and so since my rank here is odd, then I'm going to send and receive with my odd rank. Right, and if my rank is, if I'm in an even phase, then I'm going to send and receive with the even rank. Okay, so then this is going to do the communication between the pairs of processes. But after you do that communication, you need to do this sort of merging process, right? Because in general, you could have multiple values and you need to merge these. Okay, so the final part of this is to call this function called compare split. Okay, so this compare split function is basically going to it's going to do something like merge sort. Okay, so I'm not going to go through this in too much detail, but you can look at this, and basically what you're doing is you know, so if you have two sorted lists like this, right, then you know that you can combine these into one big sorted list with all of the numbers, right? So that's basically what you do in merge sort at every layer of recursion. Okay, so we're going to combine this into one big list, and then if you're like the sort of the left process, okay, the smaller of the two processes, then you're going to take the where is it? Okay. Then you're going to keep the smaller elements. Okay. If you're the left process, you're going to keep the smaller elements, and if you're the right process, okay, then you're going to keep the larger elements. Okay. So then, yeah. So we do n phases of this. Each phase is we send and receive between the right pair of processors, and then we call this compare split function to keep the right set of values.